talking to you from Melbourne, Australia. I would like to thank the Sri Lankan Geotechnical Society, in particular the organising committee, for asking me to provide this presentation today. I'd like to acknowledge my co-authors, Dr. Andrew Lock-Hayden and Mr. Alex Henderson. So I'll be talking about foundation investigation, design and analysis for high-rise buildings. Before I start, I want to talk about safety. What you can see here is an excavation about 12 metres deep done in siltstone in Melbourne. You can see footings have been cut into the base of the excavation, and there's reinforcement placed and so on. So there's definitely people been working down here. There's no support provided to the walls of the excavation at all. And yes, you got it right, it collapsed. No one was hurt, or injured, which was fortunate. It collapsed shortly after people were in the excavation. Obviously, you can see this building is in a perilous condition. The engineers, the structural engineer and geotechnical engineer, were both prosecuted under the Health and Safety Act and found guilty. Here's another case where we had an excavation in Melbourne and in fissured basaltic clay. Two young people got down into the excavation to clean out the base for some pipes. The excavation collapsed and they were killed. So I would implore you to, when we think about and design, especially excavations in the ground, which are quite often needed for high-rise buildings, we think very carefully about safety and design. We can stop this happening, and it's up to us to help. So my presentation today, I'm basically going to be looking at footing design, and I'm going to be talking about designing for serviceability, how we use soil structure interaction, what ground investigation we should do, and about proving new performance, and a little comment at the end about what we provide and how we deal with structural engineers. So there have been many high-rise buildings built over the last 50 years or so. So there's widespread experience. Most of these buildings have performed satisfactorily. Why have they performed satisfactorily? Probably because they're based on experience. There's a fair amount of prudency in design, and the construction has been satisfactory. However, have we got complacent? Are we over-engineering? Has local experience and precedent limited innovation and stopped us from doing more efficient designs? Well, I think so. I think there's so many local ordinances and so on that define what we should be doing for footings, which have come from very conservative practice. So how can we use modern tools and knowledge to make more efficient foundation systems while retaining prudency and satisfactory performance? With footings for high-rise buildings, we've basically got three types of ground conditions, and the footing solutions are tailored to dealing with those ground solutions. So the simplest by far is we've got competent ground at the surface, relatively high stiffness and strength, sufficient such that we can use pad or surface footings, strip footings, rafts, footings and so on. We generally just need to design, because the ground is so good, we just generally need to design for the individual performance of the footings because group effects are minimal. And we need to design for settlement. And I asked you how many actually you design for settlement. You probably design for bearing capacity, maybe check settlement, but how conservative are you being? Then we've got competent ground of intermediate strength and stiffness, which at the surface, which then stays constant or improves with depth. Now, this type of ground conditions are ideal for piled rafts, piled pads, piled strips, or what I call combined footings. In these, the individual performance of the footings are important, but so are the group performance, the interaction between the piles and the raft, and in between piled footings under different columns. Settlement again governs. We generally need to go to advanced soil structure interaction analysis to design these completely. And then in these systems, the piles basically have to act as settlement reducers, and the bearing capacity is of the combined system, not of individual elements. The third which is also fairly straightforward, is where we have fairly weak material down to a certain depth, which then can form a reasonable founding depth or founding material for piles. And there's different forms of piles you can put in. Because the piles tend to, in many of these cases, tend to bear on reasonable material, the individual performance of the pile or a small pile group is generally all we need to do, because the group effects between different pile groups aren't usually significant. For high-rise buildings, for super tall towers, yes they are, but for high-rise buildings it doesn't tend to be too significant. The settlement again governs, and the diameter of the pile is maybe need to be larger where we have weak ground conditions near the surface. So what are our footing system requirements? Obviously we need to design the footing to sustain the vertical and lateral loads without moving too much and without accelerating too much. It can't collapse under earthquake or ultimate wind load conditions. Must ensure minimal impact on adjacent structure and assets. Must be sustained, durable, cost-effective and safe and practical build. How often do we think about sustainable and practical to build? These things that I will talk about a bit more briefly. We consider available construction equipment and raw materials. There's no good building or designing a footing solution which you can't build because you don't have the raw materials or the equipment. We must comply with local authority requirements, and many of these can often be very conservative. So there's an education process which needs to be gone through. And you must design the footing so it requires no maintenance, because it's very expensive to do any repair works on if required. So the summary of all that is the satisfactory performance of a high-rise building is reliant on the satisfactory performance of the foundations. And so everyone in this audience, if you're designing these types of buildings, the geotechnical engineer is the key. I mentioned safety in design, and I had a safety issue up front, but this is another one because I think it's important. This is the lift overrun pit in a basement excavation for a high-rise building. It's in very low strength to low strength siltstone, which was essentially horizontal bedding, and there wasn't expected to be any instability issues around the core. So, you get people down here cleaning out and doing stuff. But obviously in this case it failed. And it failed because there was a hidden dike behind one of the faces, which wasn't obvious at the surface or obvious in the face of the excavation. There are always hidden things in the ground. And so we need to find a better way of doing this so we don't put workers at risk. There are better ways. We can use soil nails, we can batter this back. We can use different types of systems. So in this case, no one was hurt and we're very fortunate. But you can do a similar thing for footings. I mean, shallow footings, do we get people down them? Do we need to get people down them? Can we clean them out by using a sucker truck? Can we put in prefab cages and so on? With pile holes, do we barricade them? Is the site big enough to allow piling room to work safely without impacting on other workers and so on? So we need to think about all these things. The second issue, which we often do not think greatly about, is sustainability. And by sustainability, I mean the efficient use of materials and equipment. So we get a design optimization, we can come up with a practical design solution, we reduce waste and limit disposal to landfill, we reuse materials where at all possible and acceptable. And you might want to think about footings as heat inverters, which works very well in the colder climates. I'm not sure how it would work in Sri Lanka, being a nice warm climate. But all these things we need to think about. So this is why we need to push for more optimization with respect to our footing solutions. When we turn to design, I'll just look at the design of shallow footings, design of piles and design of combined footings. So with shallow footings, it usually requires very low strength rock or better. You can put rafts or buildings of medium rise of limited height on rafts on hard clay, but generally the settlements start getting a bit high. So when we talk about the Most pads, when we design them on rock, it's based on a bearing capacity. But bearing capacity is quite difficult to assess in rock, and it's going to be settlement which governs anyway. So Pels gives some guidance on this, although his guidance I think is reasonably conservative. He estimates or recommends a value of 0.5 times UCS to limit settlements to 1% of footing width. I tend to use a value of 1 times UCS, and I then check settlement and bearing capacity, where the bearing capacity is basically affected by the rock structure more than anything. Because settlement governs, and in rock and the loads, the bearing pressures are usually reasonably low, elastic solutions are usually adequate, because remember, we're only 1% of the UCS of the rock. You need to think about minimum footing size, and may be limited by construction considerations. It's no use designing a footing which is very small and can't be practically constructed, or is smaller than the column dimensions. And there's been several cases where I've just said, put a footing, what is actually the column cross-sectional area, and I design the footing accordingly. It's just a slight outstand for the column. The inspection of footings is a necessity, and this is to confirm design assumptions, because if they don't clean out the footing properly, or your design assumptions are wrong, the footing won't perform as designed. I generally do not require potholing in the base of footing excavations. That's just drilling a shallow borehole to assess whether there's any weak seams below. You can usually assess this from the ground investigation if such weak seams are likely, looking at the understanding the geology of the site, and looking at the sides of the excavation, floor of the excavation. In strong massive rock, is a footing actually required, or can you get away with just drilling starter bars and placing blinding and going up from there? With footing, with piles, the choice of pile decides on the ground conditions, and you need to design the pile to suit the ground conditions. I tend to start with selecting the diameter based on structural actual loads or bending moment. I then use geotechnical considerations to design the or the length of the piles. When you're thinking about the diameter of the pile, just remember that usually the smallest diameter which carries the structural load is the most efficient, simply because the smaller diameter piles are more efficient with carrying load than large diameter piles because of shaft resistance effects, which I'll talk about in a moment, and they're easier to install. And it's quite often better just to have one pile under a column than a group of piles, simply because with a group of piles you need a pile cap. But if you're having a group of piles under a column, you don't have to place them in 3 diameters. You can place them very close together. You just need to take into account the interaction between the piles when doing so. And quite often it's better to place them actually quite close, like 100 millimeters clear spacing with a smaller pile cap to get satisfactory performance than placing them 3D apart. But equally well, you can just replace them by one large diameter pile. In soft ground, where you've ground at the top, the pile diameter may actually need to be increased to carry the lateral loads. With CFA piles, just remember reinforcement to about 20 metres depth, so if you need full length reinforcement, CFA piles may not be applicable. Assess the pile length based on geotechnical capacity or geotechnical performance, noting that settlement governs. And I tend to put about 70% of the working load on the shaft, unless I can prove the base resistance can be achieved. Most of our pile design is over-conservative. We tend to underestimate pile performance, but the reason we get it wrong is usually because of construction effects and integrity issues. We rarely under-design a pile, but there are circumstances where you can, and people have, so you still need to do the proper analysis and so on. When we come to combined footings, you're basically designing interaction between a shallow level footing and a pile or a series of piles, and the whole process revolves around putting about an equal load on the piles as you do on the shallow footing, maybe a 40 to 60% split or 60 to 40% split. I generally preliminary size these by doing an independent pile analysis and a shallow footing analysis, and distributing load as necessary such that I get a compatibility of displacement. Once I have that, I select the pile diameter as per the previous slide, defining the pile diameter by structural capacity, and I then adjust the length and pile spacing and footing size to achieve the compatibility of movements between the two. And I just keep adjusting as required to achieve settlement and bearing capacity requirements. So you can do this all in a spreadsheet, using hand calculation. When you're doing this, you need to do your best estimate of settlement performance, not a conservative estimate. Don't use factored values. Use prudent, conservative, best estimate parameters. I then undertake final sizing by soil structural interaction analysis. There's numerous programs you can use. I tend to use Plaxis, but that's, there are many programs available. I put the piles on the main load-bearing elements to reduce the bending in the raft, otherwise you can end up with very thick raft thicknesses. Just remember when doing this, if you keep extending the length of the piles so they go into a stiffer layer, they will attract more load, and therefore you will need more piles, and therefore you're tending towards a pile solution, so you can tend to chase your tail a bit. The bearing capacity check is I do last, and it's not for the individual components, it's for the whole system. In doing so, the piles are generally working quite hard because you're trying to match the settlement between the piles and the raft is working less hard. So that if you're looking at a factor of safety in the piles, it's probably the order of 1.5 or something like that. On the geotechnical capacity, structural factors of safety you need to still maintain, but overall the raft lifts the factor of safety up considerably. So all of these factors have, or the main design situation, either you end up with piles in rock or footings in rock. To design these, I think of them as a 4-stage process, which involves the ground investigation and testing of the ground, the analysis and design of the footing, whether it's a pile or a shallow footing, the construction of the footing, and the confirmation of performance. Every one of these aspects will take a whole talk, and I will just deal with them very briefly. So if we consider axial load only, pile resistance comes from shaft and base resistance. Obviously, a shallow footing just comes from base resistance. Now, the mobilisation rates of shaft and base resistance are different, and both of them depend on many, many factors. So we need to consider those factors to understand the performance of piles and shallow footings. With piles, the pile integrity is paramount. If you don't have a pile which is integral or not constructed properly, the pile will not perform as designed. And pile integrity is completely independent of geotechnical properties. So that means construction is paramount. Pile underperformance is usually not due to inappropriate geotechnical design, but usually due to poor construction. So if we look at pile and base resistance, pile, base and shaft resistance, they mobilise at different rates. For instance, a pile shaft resistance mobilises generally about 1 to 2.2% of diameter, whereas base resistance keeps improving well up to 10% of diameter. Settlements reach 10% of diameter. So you just can't get your shaft resistance and your base resistance divided by factor of safety and add them together. That only works at the ultimate capacity of the pile. What you need to do is think about settlement and do a settlement and mobilisation analysis. So let's look at base resistance first. Intuitively, if I have a shallow footing at the surface, for that footing to fail, the failure surface must exit to the surface. And so, I mean, I'm talking about footings in dense dilating materials such as rock. And so you can see that there is probably a limit to the bearing capacity. When I get a deep pile, with respect to base resistance, the pile loads the ground below the base of the pile, and this material, as the load on it increases, will start shearing, and when it shears, it dilates, so it grows bigger. So that bulb expands against the surrounding ground, which pushes back on it and makes it stronger. So therefore, for this to actually cause failure, this failure mechanism, or this stress bulb, the failure surface must head all the way to the surface, because this material keeps dilating. So you can see that intuitively the bearing capacity of a deeply bedded footing or a deeply embedded pile will be very, very high. So, and in fact, it's usually too high to practically measure. And in the literature, if you look, the pile tests which have actually achieved ultimate bearing failure generally have a length less than 2 pile diameters, in which case the bearing capacity is usually about 5 times the unconfined compressive strength of the rock. As soon as you get greater than about 5 pile diameters, the ultimate bearing pressure gets well above 10, and it's very difficult to measure. When I say above 10 times the UCS. And it can be, there's measurements being made of 30 and 40 times the UCS. So the end bearing capacity is very high. So, but the thing to remember, it happens at large displacements, which are too large to satisfy serviceability limits. So we must do this settlement analysis, because settlement is critical. The other thing to remember is that ultimate geotechnical base resistance is usually greater than the pile structural capacity, the strength of the concrete for rock strengths greater than about 2 to 3 MPa. So once you get into rocks of greater than 2 to 3 MPa, it's no use doing a bearing capacity check for a pile, because the pile structural capacity of the column itself is exceeded, will be exceeded first. So these values up here were achieved under ideal research conditions, where pile bases were completely free of debris. Once you introduce debris into the base, of course, your settlement will go up for the same load, because the debris will compress. But ultimately, you will still achieve the ultimate bearing capacity of the pile, even if debris is there. It will just take more displacement to reach it. So this is why I think piles need to be designed on the basis of settlement, not on the basis of assessing ultimate shaft resistance and ultimate base resistance. The pile resistance is developed, pile shaft resistance developed as a frictional response on the interface. There is some adhesion due to the cementation coming out from the concrete, but that's generally broken at very low displacements, and it's very variable, and so it's not usually relied on. There are a number of factors which affect it. You can see there's 2 factors in this: is a friction angle and a normal stress. The normal stress acting on the side of the pile is dependent on the fluid weight of concrete, which we're pushing against it, how much the pile rock interface dilates during when the pile settles. That dilation will cause the pile socket to push out against the rock, which will increase the normal stress, which will increase the resistance. Now, the amount of dilation depends on the diameter, on the roughness of the socket, and the increase in normal stress depends on the stiffness of the rock mass surrounding it. The other factors which affect it are the rock type, which will affect the base friction angle, the minerality and so on, which affect the base friction angle, and the intact strength of the rock. The intact strength of the rock is actually a minor component, and it's all these other factors which have a large effect than the intact strength of the rock. The intact strength of the rock, however, is a fairly good indicator of rock mass modulus and other things, or it can be, and that's why it's used. It's something which is easy to measure and correlate with. We can also get a reduction in this resistance, shaft resistance, if we've got smear or residue, bentonite filter cake on the interface. That's why you need to clean it off. We don't tend to get these smear or residue with use of polymer. So shaft resistance, there's lots of empirical correlations in literature. This is one of them, where you plot an adhesion factor against the unconfined compressive strength. And this variation, it's an order of magnitude variation, is due to all those factors. And so unconfined compressive strength, like I said, is an indicator. It is not the only thing that affects shaft resistance. So as a designer, you get to choose whether you want to use 0.2 times the square root of UCS up to 0.45 times the square root of UCS. Where you are here really depends on how well you know, or the piling contractor, how the piles are going to be put in, what quality assurance mechanisms you put into place, whether you're doing load testing. There's a whole lot of factors. And so you need to make an estimate as a designer. But that estimate must consider the construction, because if it doesn't, you could get it very wrong. Rock discontinuities, these tend to be taken into account when the assumption of mass modulus. So you really don't need to double count them. So going back to the previous slide, if you automatically, while you've got UCS here, you might have a highly fractured rock down here, and you might have an intact rock up here. It's something you consider in selecting your shaft resistance value. So overall, when you doing pile design capacity, just remember the traditional approach with a base resistance divided by a factor of safety and the shaft resistance divided by a factor of safety are not valid for long sockets. They're okay for short sockets, but they're not valid for long sockets because of different mobilisation rates. So the design approaches need to consider settlement and different mobilisation rates for both shaft and base resistance. There are several methods you can do this. There's RATS, there's a method I use called Rocket. There's several others. There's no preferred method. You just have to make sure you get the mobilisation right and the rock mass properties and the shaft and base resistances estimates reasonable. Excuse me. With respect to construction governs everything. If you don't get the construction right, the pile will not perform as designed. So most piles fail in rock because of integrity issues, in other words, poor construction, not geotechnical strength issues. There are many ways to install piles into rock, so as a designer, you should be checking the method statements of the pile designers and making sure that they're going to install the piles such that you achieve the pile that you have designed. And then you need to check because of construction phase services. You need to check with construction phase services to make sure you've got the footing you have designed. For instance, here's an example of two footings in the same site in Melbourne. This one's in good siltstone, nice and clean and so on. That footing will perform as designed and probably better than designed. This one is dike affected. If you're not there to assess this and reshape the footing or do whatever you need to do to clean out this footing and make sure it's correct, it will not perform as designed. With piles, it's a bit more difficult. You can't really see what's at the base of the pile. Here are some examples of things that can go wrong. Here you've got a lot of debris at the bottom of a pile, which has obviously fallen in. They haven't cleaned it out. You've then got issues with the trimming of the pile. Same here, you've got defects introduced here from perhaps material falling, injury, concreting, and so on here. None of these piles that they're carrying actually a load will perform as designed. So this is why you need construction phase services. If I turn now to the ground investigation, it's a several step process. Many people just go out and do a ground investigation without understanding what the geology is and so on beforehand. To start off with, go and research the geological history, understand how the ground is formed, and from that you can develop a conceptual ground model. And once you have the conceptual ground model, you can then understand what type of footings you're likely to need. It will also help you identify the risks associated with the works. And based on this information, you then go and scope the geotechnical investigation. If you've got a uniform site, you don't need many boreholes, and you tend to use your boreholes and do a lot more testing in those boreholes, high quality testing, such that you get a better idea of the low deformation behaviour of the materials you're going to be founding in. If you've got a more complex site, then of course you need more boreholes and you might have to cut back on your testing. I like to concentrate on in situ testing because I think it gives you the best bang for the dollar, so to speak. And I target these to assess stiffness and low deformation properties in the area of influence. You know, typical tests I might use are CPT and dilatometer in reasonably weak ground. Then in stronger ground, I use pressure meter and cross-hole seismic testing. And of course, if you can do pile load testing beforehand, that can also be of great benefit. When I'm drilling boreholes, I tend to use auger through the soil materials, of course, but as soon as I hit material which is even extremely weathered rock, I start using triple tube coring. I use triple tube because you get good recovery and you get a much better sample. Augering to auger refusal and doing SPTs is of very little value when you're assessing footing design. And if you only have this information hand, you tend to be very conservative. To give you an indication of the difference between double tube and triple tube coring, you can see here these were two boreholes drilled into basically similar locations at the same site. You can see the differences in the sample you achieve. Once you achieve samples, you think about what laboratory testing you should do. I tend to just do them for intake strength. Many of the other types of laboratory tests you can do are of little value for foundation design, so don't do them. And spend your money on where it's, on more useful tests. Once you've got all this designed, you then undertake the geotechnical investigation, the testing. You develop your geotechnical model, go and including your design parameters, your best estimates, go and do your design, and then build your footings and do construction phase services. To give you a couple of examples, this was a case we did in Mumbai, India, where we had deeply weathered pyroclastic rock. The design was for large diameter, very deep bored piles, and that was based on a ground investigation where they did auger to refusal with SPTs, then single tube cored boreholes where they had a very large core loss, and so that was the design they came up with. The developer didn't like that and asked if we could do something more efficient. So we said, well, that's fine. We went and did a ground investigation where we had only a few boreholes. I think there were 7 boreholes done. Within those boreholes, we did cross-hole seismic testing and we did triple tube coring and pressure meter testing. And these are the results from the cross-hole seismic. You can see them here. This is actually only one result, and it's using different factors. What you have to remember is that, so this is modulus across the top. The cross-hole seismic is small strain modulus, so you must correct that modulus for engineering strain levels, which are typical for the foundation design, which are more akin to pressure meter value modulus, which are given by these lines here. And this is the stratigraphy we assumed. We would have liked to have dropped the basement another, 4 metres or so, and that would have meant that this pile graph would have behaved more efficiently. The basement level was set at this level, and so the final design ended up with 81.2 metre diameter piles, so 21 to 32 metres long, and there was a sharing of load at working load between 30% of the raft and 70% of the piles. If we would have brought the raft down deeper, that would have become more even. This is another case where it was the first tall building in Darwin in Northern Australia where it's a deeply weathered phyllite, and you can see a sample of it here. This was using triple tube coring. The material slakes basically as soon as you dig it. We tried doing pressure meter testing in it to no avail. The original investigation called for large diameter, very long piles, and I questioned how you could actually drill piles and get reasonable resistance in this type of material. We were asked to look at whether there was any other alternatives. So we looked at the geology. It's very old. It's very compact. It's just weathered. So we were expecting material with quite low void ratio, which therefore wouldn't settle very much. So to prove it, we went and drilled some 600mm diameter holes. We dropped some precast piles into it. We then dynamically tested those precast piles, which were basically only carrying base resistance. We did that at various depths, and from that we will be able to assess a modulus profile for below the building. We then designed the building for shallow foundations, where we had to put in special consideration to stop so the footings were dug and quickly blinded, so this type of sloping didn't happen. And then they built the building, and it all went very well. And the settlements of the building were very, very low. Once you've done your preliminary design and so on, with certain types of buildings, you will need to use soil structural interaction. My general rule with soil structural interaction is keep it simple. Many people just go off and do three-dimensional finite analysis initially, and most of the time you don't need them, certainly for just high-rise buildings. As they get taller, you do, but for lower-rise buildings, you don't. So let's keep away from the complex methods unless you really need them. Simple methods give you certain advantages, which you can use, and they can also be used to check more complex methods later on. One of the most important aspects of the SSI modelling is your constitutive models plus, in other words, your geotechnical model and your geotechnical parameters. So again, keep it simple. Pick the constitutive model which gives you or captures the main features of behaviour that you're important. Do not go over complex because it's very hard to check, and it probably won't make a lot of difference to your answers. And of course, engineering judgment is required. The important thing is that you must use proven best estimate, not factored soil properties. So we factor the outputs, not the inputs. We need to get the best estimate of that we can. So with shallow footings and piles, there's a range of analysis methods you can do. You can do 2- and 3-dimensional analysis, finite analysis or similar, to look at group effects and so on. And that's a whole other lecture, so let's not go there. But be aware how these programs actually model the behaviour of piles and so on. So this is base resistance, shaft resistance, modelled in Plaxis using embedded beam and the volume element. You can see that the shaft resistance was modelled reasonably well. The solid line is the actual pile, whereas the base resistance, it predicts that the pile would plunge. So you need to do something in the model to bring these back up to here. So you need to model individual piles before you start looking at groups of piles. Finally, with the interaction with structural engineers, you need to remember the structural engineers tend to think of foundations as soils and springs. We tend to think of it as a continuum. So with foundations and springs, you get very different performance if you use constant springs than you do with a continuum model. And this just demonstrates that if you have 5 springs here, you'll get a bending moment of the raft which like that. You'll get a uniform displacement, pretty well uniform displacement. The more springs I have, I'll get completely uniform and almost no bending moment, which couldn't be further from the truth. So what we need to actually do is provide the structural engineer with a series of springs or a range of spring values which depend on location, depends on loading pattern and so on. And the whole idea is that they do their analysis using the ETABS model or whatever, using the spring stiffness values you're given so that they match the displacement you get from your SSI analysis. It's no good giving them just one spring stiffness value. So in conclusion, I've talked about investigation and design for high-rise buildings. I've talked about the importance of geotechnical investigation, designing it, understanding geology in the design, and targeting material low deformation properties rather than just strength. With design, I've talked about simple approaches. I've talked about understanding construction effects and the use of soil structure interaction analysis. The construction services is a definite requirement to ensure that you get the footing system you design. And when we provide information to structural engineers, let's make sure it's the relevant information. Just in case of spring stiffnesses, it's a range of spring stiffness values. I thank you very much for listening. I wish. Thank you.